Hi everyone, it's Mr. Sinti, and today I'd like to chat with you about pH. It's one of the more important concepts of chemistry, and it's related to water, and it's a fascinating concept in and of itself, but I'm going to take this notion of pH and the scale of pH and what is an acid, what is a base, and attempt to connect it to some important ideas that we need to consider in the biological sciences. And so let's begin this investigation. Let's just jump right in. So, one of the things, just to review this whole notion of hydrogen bonding or the cohesion of water to water, you might be familiar with the fact that water sticks to itself. And so there's a hydrogen bond. And one of the things that is of interest is that in a glass of water, you have, again, like many molecules of water floating around, and they're connected together through hydrogen bonds. They're breaking and they're forming, they're breaking and they're forming, right? But on occasion, and this is where pH comes in this, on occasion, what will happen is this attraction between two water molecules becomes really intense, and there's a little shift of a proton from one water molecule to the other. And if there's a shift of a proton from one water to another, what you get is, when the two waters, you get a hydronium ion. So it's an addition of a proton. So it's water plus a proton. And so the way you would symbolize that is you bring the H over. So it's H3O plus. So it becomes an ion, a cation. And if you lose a proton, obviously there's an electron remaining on the other water. And so that would be a hydroxide ion, which is negatively charged. And of course, if this is happening, for every one hydronium, you have one hydroxyl. How could you have other? If you had 5 of this, you'd have 5 of that. You have 10 of that, you'd have 10 of that. And so this is what forms on occasionally in water. And so let me see if I can illustrate that a little bit better, just to sort of show what's going down with that. And so let's go blue here. And so what happens if you recall? Okay, so let me just focus on that proton of this water. So here's a proton, and here's the electrons, like this. You see that? Like that? And so these are polar covalent bonds. And so occasionally, this water molecule with its free electrons over here, occasionally it gets so attractive that it's actually going to kidnap that proton. So if that proton jumps ship and goes over here, so a proton, what this becomes is H3O plus. That becomes a hydronium. And then this over here, since there's an additional electron, now this becomes OH minus. And so these two ions are formed. And the concentration of them, these are concentration brackets, the concentration of these are of course equal. And so what I'm getting at is, if you have a water molecule and another water molecule, occasionally this will break down into a hydronium ion and a hydroxide ion. You see how that can work? And so what's interesting about this is, again, if you had this, just to illustrate it one more time, if you had a water like this and another water like that next to it, what would happen is, literally this proton comes over like that. Oops, comes over, and I'll put it right here. Just the proton comes over. So you get hydronium ion forming, and as a result, you get also a hydroxide ion forming. So these are balanced. And so this is the basis of pH. Now what's interesting is, I'm emphasizing this, when this happens, it's rare that it does happen, but when hydronium forms and hydroxide form, they're in equal concentration. Okay, just want to emphasize that. And so more of a simpler way to approach this is to say that one water breaks down into a H plus and an OH, although that isn't really the case. But these would be equal. The reaction's reversible. You can go back to water. And so, as it turns out, at equilibrium, the concentration of water molecules are way more than hydronium and hydroxide ions. And you're like, okay, so it's an on occasion kind of thing. So let me just throw out a couple numbers because it's fairly relevant in this discussion. So in pure water, distilled water, no solute at all, only one water molecule in every 554 million can dissociates like this. And so when you actually measure, if a chemist actually measured the concentration of hydronium ion or hydroxide ion concentration at 25 degrees Celsius at room temperature, it would be a minuscule 1 times 10 to the negative 7 molar. So this is fairly important, this number. And so let me just spell it out. So the hydronium ion, remember these are always equal, and hydroxide ion, when these form, the concentration is 1 times 10 to the negative 7 concentration, extremely small. Likewise, it's also 1 times 10 to the negative 7 molar. Okay, so collectively these add up to 14. Okay, so because hydrogen and hydroxide ions are very reactive, okay, in other words, when these things form, they can be very reactive. And so if there's a lot of hydrogen ion or hydroxide ion, it could really affect the other biological molecules of the cell. And let me give you an example of that. So just adding a solute to a glass of water. So this is kind of part of our discussion today. Is like if I have a glass of pure water like this, and most of it is a molecule of water, okay? Most of it's this. But again, jump ship, and then we're going to form hydronium ions and hydroxide ions, okay? And these are equal in concentration. What are they? 1 times 10 to the negative 7 molar. But if I were to add some kind of chemical, let's say I have some sort of solute over here, and if I add that solute and I increase the hydrogen ion concentration like that, I will have created an acid. So the increase, something that donates hydrogen ion concentrations, is by definition an acid. If I had a different solute and I added that and it increased the hydroxide ion concentration, it would be considered to be a base. That's one definition of an acid or a base. My point being, if there's a lot of acid in the solution, this will affect other organic molecules. Like if, for example, this is an organic molecule, say this is a protein. And you're like, well, what's that have to do with proteins? Well, the shape of a protein is very critical. How a protein's shape affects its functionality. So if you alter the shape of the protein, you'll alter its ability to function properly. So you're like, well, what are you getting at? Well, if a solution becomes extremely acidic or extremely basic in terms of the scale, and I'll get more into this, it could affect the shape of the protein. A protein is a long chain of peptides or a long chain of amino acids, but that's just the primary structure. The secondary structure is often helical or sheeted. It's called the beta structure. And so you have either the secondary structure can either be an alpha helix or a beta pleated sheet, but it's held together by either covalent bonds between amino acids, as you can see here, or hydrogen bonds between polar amino acids, or there could even be ionic bonds holding it together. So if the solution becomes dramatically acidic or dramatically basic, this will affect the bonds that hold the overall shape of the protein. And so acids and bases can affect protein shape. And so I just wanted to point that out. And so organisms are sensitive to pH change. And so you have to go under the assumption that whatever the pH is in the particular place in the body, like for example in the stomach or in the mouth or in the intestine, those proteins, often enzymes, have evolved in that environment. And so any dramatic change to that, and it would be harmful. And so again, an example of a solute that can be added to water to affect its pH is something called HCl. HCl is sometimes called hydrochloric acid, as you may know. So it turns out that that's held together by an ionic bond. And so when you put it into water as a solute, it dissolves, water being the solvent. It will disassociate into hydrogen ions and chlorine ions, which then increases the hydrogen ions in the solution, and so therefore it becomes more acidic. So therefore this is a H plus donor, hydrochloric acid, so therefore it's considered to be an acid. And so what? Well, the hydrogen ions might interfere with the bonding between amino acids. And if it affects the bonding between them, not the peptide bonds per se that hold the primary structure together, but the R groups that hold the overall shape together. When I say helix, this is what I mean by helix. So if you affect the overall shape, you might affect the overall function. And so this is what I'm saying. When I say organisms are sensitive to changes in pH, this is what I'm getting at. The pH, whether it be a strong acid or a strong base, if I added this, you would get this kind of thing happening. You would have an increase of hydroxide ions, and hydroxide ion, since it's negative, will also affect the R group interaction and therefore alter the shape of the protein. So this may not be good if you want your protein to stay the same. And so the addition of an acid, likewise the addition of a base, will affect the protein shape. So the addition of an acid makes the solution more acidic. The addition of a base makes the solution more alkaline. And so when you're discussing that, let's do that. Let's talk about that. So if you had a glass of pure water and you added this chemical, I mentioned it a second ago, potassium hydroxide. And so this is held together ionically. So over here you would think, the only thing holding this together is the attraction between potassium and the hydroxide. So when I throw it into water and dissolve it, it breaks up into K pluses and OH minuses. And so overall, that is going to increase the concentration of OH. Do you see that? That's going to increase OH because this is disassociating. And so in a glass of water, let me go with another color here. In a glass of water, do you recall that the concentration of hydronium was 1 times 10 to the negative 7, and hydroxide was 1 times, also 1 times 10 to the negative 7. So if I add that, that means that this concentration is going up. And something that contributes hydroxide concentration, in other words, this will then go down. This would be something like, and we can work on calculations sometime. This would go, the hydroxide would go up, like maybe it's negative 5. And if this is negative 5, then ultimately this has to be adding up to 14. So that would be negative 9. Do you see that? And so therefore, when you consider this, right here, it's turning the solution more alkaline. And you're like, well, yeah, maybe, but how does this relate to the pH scale? Let's take a look at that. Let's talk about pH scale. So any substance that reduces the hydrogen ion concentration can also be considered a base. So it's not just increasing the hydroxide, but there could be a chemical that reduces the hydrogen ion concentration and therefore makes it more alkaline. I'll get to pH scale in a second. The example of that would be ammonia. Okay, ammonia can act as a base, and you're like, okay, why is that? Well, it can act as a base because here it is, ammonia, and it can pick up in solution protons. And as it picks it up, it becomes an ammonium ion. That's right. And so if it reduces the hydrogen ion concentration, it actually is considered to be a base. That would lower the pH by lowering the hydrogen ion concentration. I'm sorry, I didn't mean to say lower the pH. It would raise the pH and make it more basic by accepting those protons. Okay? And so adding sodium hydroxide increases. So this is one way to make a base, by increasing the hydroxide. This is another way to make a base, which is to decrease the hydrogen ion. That's two ways to make a base. And so solutions with more hydroxide than hydrogen ion are considered to be basic. Okay? So let's look at this for a second. So some strong acids and some strong bases. You may have heard that before. Oh, this is a strong acid. Careful. Or this is a weak acid. Not so bad. What determines that? Well, there's some complexity. And I'll remind you, this is a biologist talking to you about acid-base chemistry. And I'm also doing it in the context of how it's important for biology. So a pure chemist, I apologize to simplifying matters, but this is okay. Try not to misspeak anything, but a strong acid is one that disassociates completely. So therefore it's going to really ionize. It's going to really give it up. So you're going to get a lot of proton. You're going to get a lot of hydroxide forming. Okay? And so what does this mean? Well, there's other acids and bases that are not as strong. They're considered to be weak acids and bases, and so they can bind hydrogen ions. They could release hydrogen ions, and it's a little bit more reversible. As opposed to just donating it irreversibly. So, an example of this weak acid base conjugate, if you will, is in the ocean, and this is rather significant as it relates to biology. So I hope you're going to follow this, and you'll remember it. It's extremely relevant. So there's a chemical H2CO3, and it's called carbonic acid. And you're like, okay, it's an acid. How do you know it's an acid? Well, when you consider this, it could break down into a bicarbonate ion, which is negative, and a proton, which is a hydrogen ion. And so in so doing, since it can break down into this, it's considered to be an acid because it's increasing the hydrogen ion. So that's the definition of an acid. You're like, well, what's up with carbonic acid? How does it form? Well, carbonic acid, I'm going to add something to this. Carbonic acid forms when carbon dioxide reacts with water. So if you put carbon dioxide into water, in other words, you blow bubbles into water, it's going to form carbonic acid, and the pH will go down. It'll become slightly acidic because carbonic acid then disassociates into bicarbonate ion and hydrogen ion, which increases the acidity. Now, why this picture here? This is a picture of the inside of Biosphere 2. It's in the ocean area inside this in Arizona. There's a huge concern these days about the ocean becoming more acidic because of the rising amount of carbon dioxide in our atmosphere caused by, you guessed it, humans. By our increase of combustion of fossil fuels, i.e., oil or coal or wood. By burning of these combustibles, carbon dioxide is increasing in the atmosphere. You may know it to be a cause of climate change or global warming because of the greenhouse effect, how carbon dioxide holds in heat, and it's causing increases in air temperature. But I'm coming at it from a perspective of that carbon dioxide in the air also can diffuse into the ocean, and as it turns out, water holds carbon dioxide quite well. And as it reacts with water, it forms carbonic acid Therefore, it dissociates into hydrogen ions, and it makes the pH not 7, it's lowering the pH to becoming more acidic. So 7 being neutral. I'll get to that scale in a second, so hold on. So carbonic acid right over here can dissociate into bicarbonate ion and hydrogen ion, and so it's considered to be weak because it can be reversible as well. And so what's interesting about it is the bicarbonate ion is considered to be the conjugate base of the carbonic acid. And what I mean by that is why this is considered to be a weak acid base is that this can take up hydrogen ions, bicarbonate ions, and become carbonic acid. Okay? And so what's interesting is if you have a lot of CO2 and water like this, it will favor the forward of this and make it acidic. Okay, hopefully that was clear. So getting to the scale, because this is important, I've been sort of wanting to discuss it, I've been dancing around it. And so this pH scale that most of us are familiar with, you know, pH scale meaning between 1 and 14, 7 being neutral. Like, where is this all about? And acid is below 7, and base is anything above 7, 7 to 4, 8, 9, 10, 11, 12, 13, 14 are basic. Where does this come from? Well, it comes from the fact that in pure water, as I mentioned at the top of the video, when water is able to dissociate, if you will, into hydronium ions and hydroxide ions, those concentrations are equal. They're 1 times 10 to the negative 7. And so collectively, that adds up to 14. If you add a chemical, and I've mentioned this before, if you add a solute that shifts the balance of hydrogen atoms and hydronium ions, in other words, you increase, like this, you increase hydrogen ions, that leads to an acid. And so if you increase hydroxide, that will lead to a base. And so opposite. So if you add a base, it's going to increase the hydroxide and decrease the hydrogen ion. So it's sort of like a teeter-totter, back and forth. And so, whoops, I didn't mean to do that. I didn't mean to do that. I would like to get that back. I'm not sure how I can do that. Let's do, whoops. Apologize for this little interruption. Let's do this. Okay. Sorry about that. Craziness. Sorry. So, so hopefully you're fine. So the hydrogen ion and the hydroxide ion concentration are typically expressed using the pH scale. And so the pH scale, as I said before, ranges from 1 to 14. And so the definition of pH is the pH is equal to the negative log of the hydrogen ion concentration. Let me write that out. So it is the pH is equal to the negative log. Log is the inverse of base 10. So it's the log of the hydrogen ion concentration. So what does this mean? This means that if you knew that the hydrogen ion concentration was in a given solution, say, I'm just making this up, say it's 1 times 10 to the negative 5. And you're like, okay, so I'm going to take this inverse of, which is the log, I'm going to take the negative 5 up here, and I'm going to simply bring it down and change the sign. So I'm going to say the pH is 5, which is acidic. Okay, so you're like, wait a minute. So all I need to know is the hydrogen ion concentration, and I'll know the pH. Yes. So let's go here. If the hydrogen ion concentration is -3, the pH would be 3. If the hydrogen ion concentration is -9, which means there's not a lot of it, the pH would be 9. That means that it's alkaline. This would mean that it's acidic. Okay, so on a pH scale, anything below 7 is considered to be acidic, and these are examples of that. Like coffee, tomato juice, vinegar, these kinds. Gastric juice is very acidic. Okay, and then over here, these are things that are alkaline or basic, like ammonia, for example. We went over that, oven cleaner. So these things down here have more hydroxide. These over here have more hydrogen ions. Okay, so this can shift depending on what you want to add. And again, like maybe you've seen a scale like this. These are kind of red over here on the side. We have different indicators, chemical indicators that can measure pH. We have probes and things like that. And so acid can be, like, for example, let me do this. I always remember that acid can often be red. That's how I remember that. And I also remember that bases can be blue, like that. And so you get alkaline and you have acids going like this. 7 being neutral, 7 being pure water. Why 7? Again, because 7 is 1 times 10 to the negative 7 for the hydrogen ion concentration. Okay, and if that's the hydrogen ion concentration, the pH would therefore be negative log of the hydrogen ion concentration. So you would just bring it down and you'd say pH is 7. And if the pH is 7, it's considered to be neutral. So the pH of neutral solution 7. So acids have things less than 7, bases have things that are more than 7. Okay? And so what you have to understand is that just the change between one number to another is really a tenfold difference. You're moving the decimal over, and so this can be a big change. It's a huge change between 5 and 4 and 4 and 3. And so, again, getting back to biology a little bit, you're like, well, what? Like, what do I care if there's a lot of hydroxide or a lot of hydrogen? Yeah, it can affect the shape of a protein, for one thing. It could affect whether or not organisms are surviving in the ocean. It can be very damaging. And then obviously, like in the soil, this can affect, if the pH is abnormal, it can affect whether or not plants are able to absorb nutrients properly. So these are all critical things. And so one of the things that organisms have in order to make sure that they're not damaged by sudden fluctuations of pH is that they have chemicals called buffers. Now, a buffer, you can have a buffer at any pH and it'll maintain that. A buffer is something that resists changes to pH, so they're sort of like chemical sponges. They can absorb, in other words, they're a chemical that can actually absorb excessive hydrogen ions. It's also a chemical that can absorb excessive hydroxide ion concentrations, but it can also be a chemical that donates hydrogen ion or donates hydroxide ions in order to maintain pH. So there are these chemical sponges, and so buffers can accept hydrogen ions or donate them depending on the need. And so an example of this I've given to you before, like for example, carbonic acid and its conjugate, bicarbonate ion, acts as a buffer. In other words, if there's an excessive hydrogen ion increase, this will accept it and be converted to carbonic acid. If there's a lot of hydrogen ions, then this will push it over, or in other words, this can donate. If it becomes basic, this can donate hydrogen ions. And so it helps to maintain the pH, a buffer does. A buffer is a combination of a weak acid base, and it helps to maintain pH so that it does not fluctuate too extremely. And so, again, I mentioned this, but I'm going to emphasize a little bit more. Unfortunately, as a result of our industry, human production in factories, sometimes we produce chemicals as a byproduct that go up into the atmosphere, and they react with water in the atmosphere and they produce acidic compounds. And then this comes down in the form of rain, and so it's called acid rain. And when rain comes down, it's not supposed to be pH 4 or pH 5. And snow is not supposed to be acidic. Fog is not supposed to be acidic. And so when it's raining and these strong acids are falling to the earth, again, what chemicals? What are we doing? Well, the burning of fossil fuel not only produces carbon dioxide, which is causing the acidification of the ocean, but the burning of coal and oil and gas in factories and automobiles also produces other chemicals like sulfur oxides and nitrogen oxides. And these sulfur oxides and nitrogen oxides can produce sulfuric acid and nitric acid. These are strong acids. And so those acids can come raining down, and they can, in the rain, like here's an example of this, the rain in the mountains of upstate New York can be as low as 4. And so that's dangerous. And so, like, even in pristine areas, like you might think, like if this is a cross section of California and this is like the Pacific Ocean, and say these are some of our national parks over here, like even though the industry is over here, the gases are carried by the wind and they move around to different locations, and so that it rains, it can hurt pristine areas and sort of kill off plant life. So these acidic gases go up in the atmosphere, this nitrogen and sulfur gases. And so what's interesting is when you look at the soil, in this area, look at this in New England, and like, why over here is it so acidic? I mean, this is really alarming. And it's because this is where there's a lot of industry. So this is where there's a lot of pollution. So what's brutal is, you're not showing Canada here. It's like Canada doesn't appreciate the fact that the United States is producing these compounds that are traveling over to their country and raining down acid. So this is a concern internationally when one country is doing something that's affecting the whole world. And so, again, what's the problem with this? Well, the effects of acid into lakes and streams can be more pronounced, especially in the springtime, because in the spring, that's when the snow melts, and so you get this big flow, like of waterfalls, and the river levels are really high, and that's when all of this acid starts getting introduced into rivers. And so that can destroy the little microscopic aquatic organisms, and it's the little guys that make it all happen. It's the zooplankton, it's the phytoplankton, it's the macroinvertebrates in the river that are most sensitive to these harsh pH changes. And if you don't have the little guys, you're not going to have the fish, and then the whole food chain gets unraveled as a result of that. And so it's really serious. And so some of our great lakes in our national park, this is Lake Tenaya in Yosemite. And what happens is the pollution comes over and it rains. And so these lakes and rivers, the Tuolumne River, we've been studying it for several years now. And I've watched the Tuolumne River go from pH 7 to pH 5. And so, it doesn't happen overnight, but it's an accumulation and it's of consideration. And again, I mentioned, like, right in the spring, it can be really devastating because the early meltwater can be as low as pH 3. And so all of this is getting into our rivers and streams, and it can be really brutal. And it can even affect the soil as well. A little complicated, but I'll touch on it briefly. If there's a lot of hydrogen ions in the soil, what happens is it affects the plant's roots' ability to absorb certain ions in the soil, and so plants can die as a result of it. So pH is really important, not only understanding like the pH scale or how does it all work, but it really relates to biology. And so I hope you enjoyed this video, and thanks for watching.